So, this is the different technical terms which are used in our tree. Okay. So, when we have a particular tree, so this A, B, C, D, E, F, G, H, I, all of these are called nodes. Okay. Here A is called root node, root of this whole tree, root of this whole tree. Now, this is a tree, and also this one is called a subtree, like D, H and I. This is a subtree, this is called a subtree, part of a tree, this is called a subtree. In this case also, D is also called root of H and I. H and I, these are called child nodes. H is called left child and I is called right child. So, in this case, in binary tree, it is actually we can here we are not discussing about the binary tree. So, it can be any child. Okay. Whenever it is binary tree, only two childs are there, then we will say this as left child and right child. Okay. But here just for these are childs. Okay. And these are called edge, A to D, the line which connects two different nodes, that is called edge. Okay. Then this tree, in this tree, A is at level 0, B, C, D are at level 1, these are called levels, level 2, level 3, and this way they will continue. So, if I ask what is the level of G, G is the level at 2, at second level G is existing. The E, F, G, H, I, this node does not have any child. So, they are called leaf nodes. As they are the end, there is nothing after them, they are also called external nodes. Here B, I, D, these are called these are called internal nodes. These are called external nodes and these are called internal nodes. Then we have if two childs, if E and I are coming from two different nodes are coming from the same parent, so they are called siblings. They are called siblings. Okay. So, this is the, you can say this is the skeleton, and this way we represent a particular general tree. Now, in this case, in general case, we have observed in our linear search when the elements are okay. So, here in our linear search we have observed we have multiple elements, and to have a specific arrangement of these elements. So, in case of linear search we have observed to search an element with the time complexity is big O of n. So, we are trying to minimize the time complexity by help of arranging these values in a particular order or a particular manner. So, how we have arranged? So, this is at, say for example, this is a node and we are trying to store these values in a binary tree. Okay, then a binary tree. Now, binary means 2. When there is no arrangement, like here is 7, here is 3, here is 9, here is 8, 11, 50, no arrangement specifically. This is called binary tree. This is called binary tree. This is called binary tree. Now, when we have a general arrangement, one node having two different childs only, then it is called binary tree. Now, whenever we are trying to store the elements like this way, one node, this is the node, it can have two different childs. A binary tree having the left node and the right node. Left node is, say for example, this is A, this is B and this is C. The condition is B is less than A and C is greater than A. Along with binary tree, this is called binary search tree. This is called binary search tree. Binary search tree. One node, one root node having its left child lesser than this and right child is greater than this. Let us have a look. If we have some element, we are getting 7, 1, 9, 8, 2, 5, 3, 10, then 6. If we have these elements, now we are trying to arrange these elements. Say for example 7. So, 7 is the condition is what? One node maximum having two different childs. This is A, this is B, this is C. B is lesser than A and C is greater than A. So, these are the two conditions. Now, let us arrange these elements or store these elements in their data structure. So, 7 is at this place. Now, 1 is coming. So, 1 will be its left child or right child? Definitely left child. So, 1 will be here. Now, we are getting 9. So, compared with 7, it is greater than or lesser than, less than. So, 9 is greater than 7. So, it is B, it will be its right child. Now, we are getting 8. So, I will again compare with 7, it is greater than 7, we will come here, here the value is already present. So, 8 will be lesser than 9, so it will be this side. Then we are getting 2, compare with 7 first, lesser than, come here, greater than 1, so it will be its right child. Then 5, lesser than 7, greater than 1, greater than again 2, right of 2, 3, lesser than 7, greater than 1, greater than 2, lesser than 5. So, 3 will be here. 10, greater than 7, greater than 9, yes, right is blank. So, 10 will be here. 6, lesser than 6, greater than 1, greater than 2, greater than 5. So, this tree, the arrangement of this tree is called binary search tree. So, this tree is called binary search tree. This tree is called binary search tree. Okay. Now, the problem with this binary search tree, now look, this problem with this binary search tree is what? If we have the values like this, if we are getting 7, then 9, then 20, then 30, then 11, sorry, 41, then 50. So, in this case we have minimized. If we make a proper arrangement, then the complexity, the time complexity we have minimized to big O of log n in this case. So, definitely it is lesser than big O of n, which is this is in this case of linear search, but in case of binary search tree we have this, but the problem is whenever the elements are in this arrangement. So, in this case, so if we try to arrange, 7 will be here, 9 is greater than 7, so its right child, 20 its right child, 30 its right child, 40 its right child, sorry 41, and then 50 is its right child. So, again if I try to search 50, how many comparisons are required? N number of comparison. Still we are having big O of n, So, in binary search tree again we are having the worst case complexity, that is not big O of log n, that is big O of n only, because this type of structure is called skewed structure. Skewed means that if the elements are coming in ascending order or elements are coming in descending order, so then again the same scenario will happen. So, to make this more efficient, we have another data structure or another structure is provided. That structure is called balanced tree, and that tree is called AVL tree. In our another lecture we will discuss this particular AVL tree. Okay. So, at this point of time, so we have discussed about the different technical terms that are used in our binary in our tree. So, these are some technical terms like what is root, what is leaf node, what is child node, what is left child, what is right child, what is sibling, what is internal node, level, what is the depth, root, age, subtree, siblings. Okay. So, these things we have discussed, and then we have discussed about what is the problem with and what is binary search tree. What is binary search tree? We have having a binary tree along with this particular specification, left child is lesser than the root and right child is greater than the root. But we have the problem that is, if in a binary tree, if you try to store the arranged element, all the elements are coming in arranged order, then still we are having some type of problem, that again we are having big O of n number of time. So, we will go for another type of tree, that is called balanced tree, and here we will learn about another tree, that is called AVL tree. Okay, whatever. In the next lecture, we will discuss about the different traversal of binary tree, the different properties of binary search tree, like pre-order, post-order traversal, in-order traversals, and what are the application of this. Then we will go for the implementation part, and then we will go for the balanced tree. Okay, thank you.